error. The relative error is the change over the initial. So the change will be ds. The initial will be s. So the change is the approximated, right, that we just determined, and s is the actual surface with no error in it. So ds was 8 pi r times dr, and the surface is 4 pi r squared. I simplify, and I get 2 dr over r. So from here, I just have to plug them in. So dr was dx over 2 pi. So 2 times dx over 2 pi. We determined it here. dr was dx over 2 pi. And now r is 42 over pi. So dx was 0.5. So 2 times 0.5 is 1 over 2 pi over 42 over pi. I'll flip. So 1 over 2 pi times pi over 42. So it's 1 over 84. I don't know if they want us to approximate. I will. 1 divided by 84, 0.0119. So what have we learned from this problem? Again, if there is a minor error in the circumference of the sphere, that will trigger an error. This is the approximate, not the exact. An approximate error of 26.738 centimeters squared. So this error in the circumference triggers this error in the surface area. What does this represent based on the correct value, the initial value? So it's the change over s. So we put the change from here over the s from here, and we simplified as much as we could. We replaced dr because we determined it in the previous step by dx over 2 pi. So there is 2 and dx over 2 pi. And I also had r as 42 over pi. Two fractions, I kept the fraction from the top and I flipped the fraction from the denominator, and then I simplified as much as I could. So that's how we use. Could I have determined the exact? Yes. Yes, I can. So I put in here, I'll find the radius for 84 centimeters, and then I'll find the radius for 84 plus 0.5 circumference, find the radius for that, and then subtract. It would have been more difficult to do that, but yes, I can. I wasn't asked to do that. I was asked to find the approximate. So final step from this chapter is linear approximations. If you remember, here's our best friend. Here is our second best friend. So this is the function, this is the point, and this is the equation of the tangent line. And remember, I said many times, why are we finding all the time so far in this chapter, why are we finding this equation of this line? Why? So I have the function. I can determine the instantaneous rate of change at p by f prime of that x value. But why on earth will I need this? And here's why. This is a line. If I want to evaluate this function near this point meaning not here, but very close, It doesn't matter that much if I use the line, the tangent at P, or if I use the function. The error will be minimal as long as the points are close to this. So if this is, let's say, A, let me give you a number, 3. So if the interval is between 2.9 and 3.2, if I use the equation of the tangent or if I use the function, it's not going to make a big deal, a big difference. So we say that this line, the tangent at P, is the linear approximation of f of x near, and we really mean that, near a point. So let's see how we do that. So I'm really telling you, that f of x is approximately the equation of the tangent line at P. Near, we say A. So this was one thing, is going to be one thing. The second thing will be uppercase L of x, which equals. So here I'm using the squiggling symbol. Here I'm using the equal symbol. This is the linear. This is the linear approximation. This is the linear approximation. I went to say linearization. So sorry, I'm going to erase this. So this is L linearization. They are the same. But the uppercase letter is called the linearization of f of x at A, and this one is called the linear approximation. Okay? So f of x is approximately the equation of the tangent, and we call that the linear approximation. And L of x is called the linearization of f of x at A. They are the same. The formulas will be the same. They are identical. So let's determine those. Again, back to our best friend. And you'll be very, very surprised. So this is f of x, and this is a point A, f of A. Of course, this is the tangent at point P. Can anyone again give us the slope of this line? The point is P, A comma f of A. And now we want the slope of the tangent line at this point. We shouldn't be thinking about this, please. The slope of the tangent line at the function f of x at point P, A comma f of A. What does this equal to?
Is that our f prime of x?
Yes, but it's not of x.
Oh, sorry, f prime of x.
Excellent. Very good. So then I want to write the equation of this line. I want to write the equation of this line at the point P, A comma f of A, knowing that the slope is f prime. Can anyone give us the equation of the line having a point and the slope?
Y minus f of A
Yes. Excellent. Equals.
equals f prime of A
Yes.
times
Times.
quantity of x minus A.
Brilliant. That's all I needed. I'll distribute. So y equals f prime of A times x minus A plus f of A. We like to write f of A first. f of a plus f prime of a, x minus a. This is L of x, the linearization. This is the linear approximation. As you see, they are identical. This one says, this is the equation of the line that approximates this. This says f of x is approximately this near a. One more time. This one says the line that approximates this function is this. The linearization equals this. The line that approximates this. This one says f of x is approximately this near a. And now I just want to show you, go back to a previous formula. I don't have my, okay, here it is. Exactly the same. F prime of a dx, f prime of a times the tiny change dx, f of a, and that approximation. So all these three are basically the same thing. So the differentials with the linearization and with the linear approximation, all the same. Okay, let's apply this. They do the linearization first. I don't want to do that. I always start with the differentials. It doesn't matter. So find the linearization L of x of the function at a. So let's choose. Okay, I will choose 3. Did I lose everyone? I hope not, please. I know it's a lot. Okay, so they want us to find the linearization. Okay, that's fine. So I know the linearization is f of a plus f prime of a, x minus a. All I have to do is to plug it in. So L of x equals f of a means the cube root of 8 plus f prime of a, I'll calculate it here on the side. So f prime of x, remember this is x to 1/3. 1/3 in front, and x to 1/3 minus 1, which is negative 2/3. Or 1/3 the cube root of x squared. So I have it right here, plus 1/3 the cube root of 64 times x minus 8. I'll simplify everything. So this has to be a line. So the cube root of 8 is 2. The cube root of 64 is 4 times 3 is 12. I will distribute 1/12x minus 8/12. 8/12, when you simplify by 4, you get 2/3. Minus 2/3 and plus 2. Yes, the least common denominator is 3. So negative 2 plus 6, which is 4. This is it. What is it? What does it mean? This is the function that approximates this function near 8. Like for 7.9, for 7.8, for 8.1, 8.001, you can use this. You cannot use it for a equals 9. It's way too far. When we say 8, close to 8, we mean very close to 8. You can use this. This is the linearization of the given function. If I use this function or I use this function to evaluate close to 8, I'm not going to get a big difference. And you can always check. You can punch in both in the graphing calculator and punch in values left and right of 8, but very close to 8, and you'll see it's insignificant or very close. That's the linearization. Find the differentials. We did this. We did this. Okay. Would you like to look at another approximation of this or not? Is it a yes?